Now, of course, beyond this, there are going to be more complicated examples. Once we start to go through the different intra-AS variations, we'll look at what happens when you're going through multiple providers. How many labels do you have when you're doing inter-AS option B versus C versus carrier supporting carrier versus the new unified MPLS? But regardless of what those variations are, it still falls back to the same simple principle that when traffic enters the network, the only thing that we're trying to do is to tunnel it to the egress edge. So the core of the network, the only thing they need to know is where did it come in? In other words, what was the ingress PE? What was the egress PE? And me as the provider router in the middle, I don't need to know what is beyond the provider edge. Specifically, as long as I know how to get between these two loopbacks of provider edge 1 and provider edge 2, I should be able to tunnel any of the traffic from the ingress to the egress. Okay, we have a couple questions here. LDP by default assigns a label to every IGP prefix. Do we really need this? Isn't it sufficient just to assign the labels for the IBGP loopbacks? Yes, that's correct. So the implementations are different between vendors and between software versions. The way that Juniper does it, they only allocate labels for the /32 loopbacks. You can set iOS XR and iOS to do that as well, but the default behavior is that whatever IGP routes that you have, you will generate an LDP label for. So if we look at this from XR's point of view and we look at the show MPLS forwarding table, whatever these values are here should be equal to what we see when we show route IPv4 ISIS. So we specifically have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 entries. This should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 labels. So the labels and the routes are on a one-to-one basis. Now, when we don't have the route through IGP, we'll see that that is going to be a problem because BGP labeling, MPLS traffic engineering labeling, and LDP labeling are mutually exclusive. There are restrictions as to what particular label numbers that you can use in order to reach a particular destination. But the feature that you're talking about, the way that you would specifically implement that, and we'll talk about this more later with LDP optimizations, but you would say under MPLS LDP label, I want to allocate global prefix or global for host routes. And let's say show run section LDP, which is this. Okay, so if we issue this command on router 1, 2, and 3, and then under iOS XR, this would be under the MPLS LDP mode. And we would say, what here? We say to label local label local allocate for host routes, this one. If we show config, so it's under MPLS LDP, address family IPv4, label local allocate for host routes. Now, from the MPLS core's point of view, though, we don't know what the final destination is. We don't know where 7777 is, and we can see this when we look at the show route IPv4 for 7777/32. We don't know about the specific destination. But what we do know is what is the exit point out of the network. The exit point is router 3. So as long as we have a label that is associated with the loopback of router 3, it means that we can tunnel the traffic over the core without them having to run BGP. Now we'll see that there's a lot of other applications for this other than just doing global unicast routing. Most of our focus later is going to be on MPLS layer 3 VPNs and layer 2 VPNs, which basically means that we would have a separate private routing table, or what we call a virtual routing and forwarding instance, a VRF, that is going to go down to that individual customer. And then instead of running IPv4 unicast BGP over the core, we're going to be running either VPN v4 for IPv4 routing or VPN v6 for IPv6 routing. But the basic principle is always going to stay the same, that the devices in the MPLS core don't need to know about the original source or the final destination. The only thing that they care about is what is the ingress router and what is the egress router. Now, if we were to look at this on the reverse path, so let's say, okay, well, we know that the ping got there, but what happens when the echo reply comes back in? So the echo reply goes from 7 to 3. This should be a native IP packet. When 3 sends it towards the MPLS core, this is where the MPLS imposition, if I can spell it, imposition, or what we call the push operation, where we're doing the encapsulation of the label. So from the packet capture point of view, we should see that the first packet was native IP. So it's the packet coming from 7777. So this is Ethernet then IP. There's no MPLS header between them. The next one is where we should see the label inserted. So we have Ethernet, then we have MPLS, and it says the label is 16,004. So we're sending from router 3 to router XR3, we're sending 16,004. If we go to XR3 and say, well, what do you do when you get 16,004? Let's show MPLS forwarding table. 16,004 says I'm going to swap it. I'm going to change the label to 16,000, and I'm going to send it towards gig 0000.1213, going towards the next hop 10, 12, 13.12. And again, where this value comes in here is, since this is Ethernet encapsulation, it's saying what is the MAC address that you need to put in the layer 2 header. So if we were to look at the show ARP and we correlate what is the MAC address of that next hop, which is 12.13.12. 12.13.12 is this 47B1 address. We should see that in addition to putting this in the layer 2 header, we're going to put 16,000 in the label field. Okay, so specifically it was this one here. So if we look at the packet capture, we should see the next frame has label 16,000, which is here. And in the Ethernet header, it should say the destination is that 47B1. So we're forwarding it towards XR2, but we're telling XR2 that you don't need to look at the IP payload. The only thing you need to look at is label number 16,000 and figure out what is the egress edge of the network. And specifically, the egress edge of the network is what? It's XR1. So we'll see that the key functionality of this is going to be based on what is the next hop of the BGP route, and do you have a label associated with whatever that value is. So when we look at the imposition edge, which in this case was router 3, and router 3 says, well, how do I actually get to the final destination? Show IP route for 8888. It says the destination is reachable via 11.11.11.11. If we now look at the Ceph entry for this, show IP Ceph for 8888/32, it says not only are you going to forward out this interface towards this layer 2 neighbor, but you're also going to insert a label value. So you basically take the IP packet, put an MPLS header on it, put the Ethernet header on it, and then ship it out the interface. The device on the other end only needs to look at the MAC address to say, hey, this is for me, and then look at the label number. Yes, I do have what we call a label switch path, or an LSP, that terminates on the loopback of XR1. So we label switch packets to XR2, XR2 sends them to XR1, and then we can finally send them to the final destination. So the end result would be the same. Let's say we ping between router 7 and router 2, or router 7 and router 10. So between router 2 and router 10, here we're running eBGP. We then have that iBGP peering that goes to the route reflector. And the route reflector has an iBGP peering going down to router 3. But again, the issue is that in the middle, XR3, XR2, and router 1, they're not running BGP. The only thing that they have instead of BGP is IGP plus LDP. So from router 7's point of view, and let's go ahead and restart our packet capture. From router 7's point of view, we're going to ping to 10, 10, 10, 10. Source is 7777 and just one packet. Okay, we should see that this is going to go how many hops in the network? It's going to go once here, twice there, third link, fourth link, fifth link, 6, and 7. So we should see from our packet capture, we have 1, 2, 3, 4, 5, 6, 7 outgoing pings, and then the one response that comes back in, 1, 2, 3, 4, 5, 6, 7. Now, if we were to pick the first one is going to be the unlabeled packet. So this is the native IP packet that came in from the customer router. It's going towards the provider edge. When the provider edge gets it, it says, well, the destination is reachable via next hop I know through BGP, and the BGP next hop points to an MPLS label. I'm going to impose 16,006, and if we look at from XR3's point of view, 16,006 should be pointing towards the loopback of router 2. And again, if we show MPLS forwarding table, 16,006 says it's really going to 2222, and we can see how many packets are specifically switched. So based on these counters here, you can tell whether the traffic is actually going through. So if we went to router 7, and let's say we send 10,000 packets, and let's say we send them with a timeout of 0, so just as quickly outbound as the CPU can generate, and we look at this from XR3's point of view, we should see the counter on this particular label switch path is going to constantly go up. So if we show MPLS forwarding, pipe include 2222/32, that's going to be the number of packets that are currently going over that path. Now, in a real environment, you're not going to see this as a real-time counter. In this case, it's a virtual machine, so everything is software switched. When you're doing hardware switching, the counters are not real-time because it periodically is pulling the line card in order to get these stats. But this is one way from a troubleshooting point of view that we can tell whether we are using the correct label, is that we know what the loopback is for the exit provider edge router, and then we should see, based on sending packets towards that label switch path, we should see that the counter is constantly incrementing. So you'll see sometimes the XR syntax is kind of confusing, how many levels deep that you have to go, but there are parallels as to what it means in terms of iOS versus XR. Sometimes it's a little bit of a struggle to see how they implemented the syntax differently in XR versus iOS. So if you know how a feature works on one of them, make sure you spend some time digging around on the CLI or the documentation to see specifically how the syntax maps to the other OS. Okay, so let's look at the change of this now. If we look at the show MPLS forwarding table, we should now only see the loopbacks. So this means from a scalability point of view, the number of labels is directly proportional to the number of nodes that you have in the IGP network, which is generally going to be much less than you have the number of links. And you could take this even a step further, because technically we don't need to allocate a label for XR2 or XR3 or router 1, because they're not the endpoints of any of the tunnels. Really, in this case, there's only 2 labels that we need. The 2 labels would be for router 3 and router 2, or XR1, assuming we have destinations reachable out that direction. But by default, if we scroll back up, you can see that the labels were allocated for the transit interfaces, and you would typically not be label switching to the transit interfaces anyways. You're always label switching towards the loopback of whatever the destination PE is. So there are optimizations like this, and we'll talk about it in more detail later. But as long as, in general, as long as IGP and LDP is on, then you should be able to have a label switch path towards the destination. Okay, there's a couple other questions here. Am I right in terms of, is the MPLS label data plane forwarding operates at 2.5 and the control plane operates at layer 4? Yes, that's correct. So if we go back to our packet capture and we look at something that is labeled, you see that the MPLS label goes between Ethernet and IP. So sometimes referred to as this is labeled, this is OSI model, or OSI layer 2.5, because it's between layer 2 and layer 3. Okay, the frame on the wire, that would be layer 1, Ethernet layer 2, MPLS 2.5, IP is layer 3. But beyond this, what I didn't show in the capture is the actual control plane negotiation, which is label distribution protocol. And LDP, if we look at the actual encapsulation of this, there's two formats for this. You have the hello message, which is UDP encapsulated. So we have Ethernet, IP, UDP, and then LDP. And then the actual exchange of the updates, which is going to be TCP based. So it's Ethernet, IP, TCP, and then LDP inside of that. So we'll talk about the details of LDP specifically a little bit later and what are some of the advanced features, what are some of the problems we can run into. But as you can see, in terms of the minimum configuration, it's very straightforward in order to implement this. So the only thing that I did on regular iOS was under ISIS to say run LDP on every single interface that you have ISIS enabled. MPLS LDP autoconfig. In the case of iOS XR, it was a couple more commands. When we look at the show run MPLS, I had to turn MPLS on. Okay, so the rest of this is not needed. This is optional. So I turned MPLS on, and then show run router ISIS. We said under address family IPv4, enable LDP on every interface that is running ISIS as well. There's another question. Instead of Ethernet, if we're using other layer 2 technologies like frame relay, how would the packets be encapsulated and sent across the destination? It would be the exact same thing. So MPLS would be directly encapsulated inside of frame relay. MPLS would be directly encapsulated inside of ATM, inside of GRE, inside of HDLC. So there's no restriction as to what encapsulation it can go inside of. And likewise, there's no restriction what encapsulation can be tunneled inside of MPLS. So what I mean by this is, and we'll look at this in more detail in layer 2 VPN, basically you can have a customer that is attached with an Ethernet segment that goes to the provider. Then you have in the middle the provider core. Okay, so this is basically, all the routers in the middle that are attaching. Somehow you come out to the other provider edge, and then on this customer edge link, you can run frame relay. For a layer 3 VPN, there's no restrictions as to what the encapsulations are. You can also do layer 2 VPNs between them, where basically you could say that this customer edge here, customer edge 1, has the IP address 10.0.0.1, and customer edge 2 has the address 10.0.0.2, and then we're essentially forming a layer 2 VPN from this loopback to this loopback, basically saying when Ethernet comes in this way, we're going to encapsulate Ethernet inside of MPLS, and then MPLS is going to go inside of Ethernet again because that's what the transport of the service provider core is. Then when it goes to the other end, it gets decapsulated and it's going to be whatever your IP packet is inside of frame relay. Okay, so the IP packet would be inside Ethernet. This is called layer 2 VPN interworking. That you're basically translating between the encapsulations, but you're doing it at layer 2. So there are other ways to implement this. There is a variation that used to be used on ATM that was called cell mode MPLS. Cell mode MPLS is basically when you directly encapsulate, and actually here's an old entry on my blog about it. It's when you directly encapsulate the label number inside the ATM, what's called the virtual path and virtual connection identifier. It's the VPI VCI, and then this basically becomes the label number. But the principle is the same, that the devices in the middle, in that case with ATM, they were cell switches that ran MPLS, and they made their forwarding decision based on the MPLS label encoded in the ATM header, and they didn't care what the payload was inside of the actual ATM cell. Okay, there's a question. It seems to me that LDP is just an application in the same sense as BGP is. Yes, that's correct. So LDP on its own is not a routing protocol. The only thing that LDP is doing is saying, take the routes that you already learned, and I'm going to map label numbers to them. I then establish a TCP session to the other router, tell the other router what label numbers I gave them, and that's all that I do. It's up to them to actually make the decision on how you're going to forward the traffic based on the routing table underneath. So this means that when you do the original imposition of the packet, okay, the imposition in our case would be on router 2 as the packet comes in this way and we're trying to get to 7's loopback. This means router 2 still needs to know what is the route for 7777. If for some reason I wasn't running BGP, I wasn't running IGP, then the label switch path is not going to build end to end. Okay, the only thing LDP is doing is saying, look at your routing table and take these numbers and generate labels for them. And then it's up to some lower layer process to actually do the forwarding decision to say, how are you going to bind the label numbers to the routes as you actually forward the packets out the interfaces. There's another question. When we are running L3 VPN, is it possible to allocate a single VPN label for all prefixes originated by a PE router in a single VRF, not a different label for different prefixes in the same VRF? Yes, you can. And we'll talk about that in more detail in terms of optimizations. But by default, Cisco's implementation of LDP allocates a separate label for every route that you learn from the customer. The problem with that, though, is that if the customer's routing table is very large, you're cutting down on the number of, or you're cutting down on the label space that you can allocate from, and it also means that you have extra hardware resources when you go to write those entries down to the line card. Because in our case here, we're doing it in software because they're in virtual machines, but in a real design, these would be hardware boxes that are basically saying, when I create the CEF entry for 7777, I need to write this down to the line card on interface gig 1, and I need to use label number 17 as I install the entry. So the issue is that the line card itself has a limited amount of memory as to how many entries that it can hold, and if you go beyond that threshold, you can't advertise any more routes. So one of the solutions for this is to say, well, I don't want to advertise a label for every single prefix. I'm going to change the MPLS LDP, what do we call this? Is it under label? And then allocate global, no. MPLS label? Label mode. Label mode is to say for what particular protocol. So for VPN v4 or for all address families, do I want to do an allocation per prefix, which you can see is the default there? Or do I want to allocate it per customer edge router, or do I want to allocate it per virtual routing and forwarding instance? So we'll talk about this in more detail when we get into more details of L3 VPN, but the point being is that the default value is that you do an allocation per prefix. So if you have 10,000 prefixes, it means you have 10,000 labels from that particular customer router. There's a question, can you tell the router not to use a label for a route? Yes, you can either filter that with MPLS LDP advertised labels. So this is basically you say for whatever this access list is, 1, 2, 3, I want to advertise labels for routes matched in 1, 2, 3 towards the neighbor 1. Okay, the other option is to say MPLS LDP label, and then I want to allocate labels globally for a prefix list. And the prefix list would match your directly connected interfaces that you either do or do not want to do allocation for. So beyond just turning it on, there are a lot of features that we'll talk about specific to LDP. But mainly what I would recommend to do for that is you need to go through the documentation section to see what features does LDP actually support. So where you would specifically find this in the case of regular iOS is under the iOS XE documentation, under the configuration guides, then under multi-protocol label switching, under LDP configuration, and make sure you go through all of these different variations. Because we'll see these, they don't directly relate to layer 3 VPN or layer 2 VPN. This is core MPLS. So we'll see core MPLS doesn't directly relate to VPN v4, VPN v6 and beyond. This is just to say, can I do the label switching from the provider edge to the provider edge? And what we specifically call this is the allocation of the transport label as opposed to the VPN label or the pseudo-wire label. So without the transport label, you're going to have a problem tunneling the traffic over the SP core, and that's what LDP is designed for. There's a question, what is the actual size of the label? I want to say it's 4 bytes. Let me double check here. So let's say filter by MPLS, and let me do another ping. Okay, so let's look at the ping. And the label's 4 bytes. No, it's 1, 2, yeah, 4 bytes. 4 bytes. So it has the label itself is 1, 2, 2 bytes, that's 16, and 4, so it's 20 bits. And then there are there's the experimental bits, which is 3 bits. The bottom of the stack identifier, which we'll talk about that later, that means penultimate hop hopping, and then the TTL. So you can see it decoded down there. 3, E8, A1, FD, since those are in hex, each of those are, no, excuse me, each of those are 1 byte. 1, 2, 3, yeah, as I said, 4 bytes. Yeah, 4 bytes total. So there is a limit to how many practically you can have in the encapsulation. And there is another section we'll talk about later, but this would be a good read in advance if you want to get ahead of the game, is just search the keywords MPLS MTU, and then there's a specific section here on Cisco's website that talks about this MPLS MTU command changes, because you do run into problems in practical designs that when you go to add additional encapsulations, you're removing the effective payload of the customer's traffic. So the customer will either need to lower their payload down, so like set the applications to use lower MTU, or you need to raise the MTU in the core of the network to make sure that you support jumbo frames. But each of the encapsulations does add overhead, and the overhead's not free. You have to account for it somewhere, either down to the application level or in the core of the transit network.